Newton's third law is kind of simple, kind of complicated in the same way, and really, really cool. Basically, what it comes down to is it's always equal and always opposite. So if you haven't read through the sheet, read through it first. I'm going to talk you through it kind of quickly. Um, Bottom line though is equal and opposite. So something like a hammer and nail, your intuition may have been that the hammer hits the nail harder than the nail pushes back on the hammer, but no, it's always equal and opposite. If we talk about astronomy, something like the force of gravity between the sun and the earth, your intuition may be that the sun puts on a bigger force than the earth puts on the sun, but again, equal and opposite. We just don't notice the force on the sun since the sun is so massive. Kind of comes back to Newton's second law, which we're going to get into more next time we do some physics. But when a mass is really, really large, the impact of the force is smaller. I want to talk you through these little charts here to make sure you get it, then I'll let you think about the end to finish. We will do, in grade 12, we do the math on Newton's third law. It's actually something interesting called conservation of momentum. So file that away for grade 12 when we come back to this. The math, we won't do the math in grade 11, we'll just sort of talk about the consequences in the scenarios. First of all, if you're going to jump straight up, you push the ground down. If, oh, sorry, and then tied into that, sorry, I should have written smaller, the ground reacts and pushes you up. That's our action, action and reaction pair. You push the ground down, that's the action. The ground reacts and pushes you up, that's the reaction. So maybe a bit of overlap. Which way do you push on the ground? You push the ground down. If the ground could move, it would move down. We don't see it, kind of like that sun-earth thing, because the earth is so massive compared to us, that little force we put on it doesn't matter. If you're on a small raft and jumped, then the raft would move down. If you're standing on thin ice and jumped, we're going to get into this later, maybe the thin ice will break. We'll come back to that when I get you to do some thinking about reaction forces. If we think about walking, to walk you push ground backwards, ground pushes you. You push it backwards. If it could move, it would move backwards. If you're on a paddleboard, the paddleboard would move backwards. If you're on a slippy floor, you may not move forward, but you may just fall. We'll come back to that again when you do some thinking. When I get you to do some thinking on reaction forces. If you're on a really slippery floor, you may push the floor backward, but it can't push you forward. Okay, last little one. If you slide to a stop, you push on the floor pushes on you, you push the floor forward. If the ground could move, it would move forward. Maybe if you've ever run and stopped on like a carpet that's on hardwood, you would slide on the carpet across the floor. If you're on perfectly frictionless smooth ice, you wouldn't stop. Even though you're pushing forward on the floor can't push back on you. That's kind of what I was looking for in those little charts in there. What I would like you to do is make sure you've read through this. Oh, for fun, don't hurt yourself. Get up, walk around your house, and kind of pay attention to when you plant your foot on the ground, which way do you push off? Then for real fun, this is actually kind of, well, I don't know, real fun. This one's pretty good. If you go to that YouTube link, there's a whole bunch of paddleboard fails, and you can see the action and reaction. You can see the paddleboard moving backwards. The last little piece I want you to think about and then answer a couple little questions. there's a limit to how big a reaction force could be. That's why you shouldn't jump on thin ice. That's why it's hard to start running on something slippery like ice. That's why it's hard to stop on something like ice. The action force can be as big as you can make it, but there's a limit to the reaction forces. So I'll get you to read through that a little bit and see if you can answer those 3 questions. As always, email if you have any questions.